Technology, Bangkok. He earned his bachelor's degree in civil engineering from the Indian Institute of Technology, Delhi, India. He is the lead author, project manager, and developer of risk-based corrective action programs for numerous states, the US Air Force in Europe, and the Israel Ministry of the Environment. Dr. Salhotra is very well versed in the site-specific application of risk assessment, evaluation of indoor vapor intrusion, natural attenuation, and fate and transport modeling for the cost-effective management of sites. Today's talk is titled Intersection of Science and Policy in the Development of Risk-Based Standards for Various Media like Air, Water, Food, Soil, and Sediments. This talk will discuss the methods used to develop concentration-based standards for various environmental media. These standards depend on the toxicity of the chemical, amount of exposure to a receptor, characteristics of the receptor, characteristics of the media, characteristics of the chemical, as well as acceptable risk to the receptor. We welcome you, sir, for the talk.
Dr. Salhotra, I'm going to share the slides to you.
Okay.
Are you able to see the screen?
Not yet.
Okay, maybe it takes some time.
So while we are getting the slides up, I'm very glad to have connected with Professor Shiva and to conduct this course. It's this lecture. It all happened in the last 2 weeks, and actually I am stationed in Houston, but actually right now I am in Spokane, Washington, on the west coast of US. It's about 8:30 p.m. here, and I'm here attending a conference on the 28th National Tanks Conference. And what we have been talking about here is contamination from petroleum contamination from gas station sites. So a lot of talk about standards and exposure and risk. Let's see if we can get the slideshow going.
Dr. Atul, your slides are already up. What I'm suggesting is maybe you can connect it to your computer with your own presentation. As you move from your presentation, slide 1, 2, 3, you can just mention to it, go to next slide, I will keep moving it. I think there is some internet connectivity issues, that's why you are not able to see, but the rest others are seeing the slides.
Sir, some slides are not visible to us.
Not, oh, it's also not visible to you. Okay, let me see that one. But okay. Are you able to see now?
Yeah.
Oh, here we go. And,
yeah, okay.
So next slide, please. And we can put it in the slideshow. Yeah. So this is the conference I was attending. You can, of course, go on to the Google and look at all the agenda and everything. But let's go to the next slide, please. So, we as environmental professional deal with many contaminated sites, gas stations, landfills, manufacturing facilities, a whole variety of chemicals, variety of media, soil, groundwater, surface water, sediments, ambient air, and even food. Bioconcentration of chemicals in our food supply is an important issue. And in the US, there are a variety of cleanup programs. But the management of pollution, management of contamination requires some standards, because that is the goal that we have to achieve. Next. So there are many different types of standards, and I'm going to talk about the first one, which is the risk-based concentration standards. There are mass-based standards, there are nuisance avoidance standards, there are BDAT, best demonstrated available technology related standards, and then there are some legacy standards which are shown to be not correct, but they are used because that's what we have been doing for many years. But the focus today is on risk-based concentration standards. So next. So the risk-based standards that we develop depend on the location. And typically, in general, we have a source and we have a receptor. Receptor is the individual, the organism, or a feature that we are trying to protect. And in between the source and the receptor, there is a media. So if we are thinking of air pollution, let's say we have a chimney that is spewing oil or smoke or some chemicals. The media is the atmosphere, and the receptor would be the individuals around that facility who may breathe that air and get exposed to chemicals being emitted by the manufacturing facility. So the two common things to remember is that we have of exposure standards, which are the standards applicable where the exposure is occurring at the receptor. And then we have point of compliance of point of demonstration standards, which are standards at any other location other than the point of exposure. So, and we will talk about this as we go along. And as chemicals migrate from the source to the receptor, they decrease in concentration. So the standard that is applicable at the source ends up being much higher than the standard at the receptor location. So this is very critical, and this is a policy choice for the protection of groundwater, air, sediments, and rivers, as you will see as we continue. Next, please. So the first, if we are talking about risk-based standards, what does risk depend on? And this is a saying from 1538, many years ago. And what basically it says is the dose makes the poison. What it really means is that uh, it's not the chemical per se that is causing the risk, it's the amount of chemical that you ingest or inhale that causes the risk. So then the next question is, if risk depends on dose, and of course it also depends on the toxicity of the chemical, then how is dose calculated, or what does dose depend on? Next, please. So dose depends on the mode of exposure. For air pollution, inhalation is the mode of exposure. And if you are talking about the risk due to ingestion of uh, cauliflower that is grown in contaminated soil, then it depends on how much cauliflower or vegetable you ingest. And those can also depend on dermal contact. So some chemicals can enter the human body by dermal exposure. So mode of exposure is the first critical piece. And then the concentration of the chemical in the media at the point of exposure. Again, the term point of exposure. And then how much air you breathe, how much vegetables you eat, what portion of your body came in contact with contaminated soil or water. That's critical. And then the last factor is frequency and duration of contact. Next, please. So there are simple equations like this for estimating the dose, which is expressed in milligrams per kilogram per day. And on a daily basis, the kilogram is the body weight, which is in the denominator. And you can see that the higher the body weight, the less is the calculated dose. And that's the reason why a child gets half the medicine than an adult gets, because the dose, for with the body weight being less, the same amount of dose requires less chemical. So the factors that contribute to the calculation are very simple: how much water you drink, how often you drink, how many days in a year you drink water from the contaminated source, how many years you continue to drink that water, and then of course the body weight, and there is an averaging time. So the equation is very simple and the science is very simple. If you breathe 20 meter cube of air and the concentration is 1 milligram per meter cube, well, 20 milligram of that chemical entered your body. So this dose equation is very simple. So in simple terms, dose depends on the point of exposure concentration and a bunch of exposure factors which are listed here. These exposure factors are different for inhalation, for dermal contact, for ingestion of vegetables, and so on. So very simple. So the science is very simple. Next. But there is the complicated thing is, and this is where the policy comes in, when you are setting standards for an entire country or entire region, there is a lot of variability in the exposure factors. Each one of us has a slightly different body weight. Each one of us drinks different amounts of water every day. Each one of us drinks water from different sources for different periods of time. So on the x-axis, you have the exposure factor, and on the y-axis is the cumulative probability distribution. So all the factors that cause any of these exposure factors from the minimum to the maximum value is applicable for some person. However, to make national standards or regional standards, the regulators have a difficult choice. What value should they use to set up the standards? Should they use the minimum, the maximum, or perhaps they should use the median value, which protects 50% of the population? So this is where the policy intersects with the science. And for those of you who are not familiar with the concept of risk assessment, if you go to the next slide, there is a compilation of various exposure factors. Next, please, which is called the USEP Exposure Factors Handbook. And if you are interested more in this subject, I'll encourage you to look at this. This particular book has, it's I think about 1800 pages or something. It keeps growing, and it has all sorts of exposure factors, mostly related to the US population: how much air you breathe, how much water you drink, how many days you spend in your home, inside versus outside, and so on, all of which affect the risk. So, which factors to use to develop a standard is a policy choice. Next, please. So, the next thing that goes into risk-based standards is the toxicity of the chemical. And we have various sources of toxicity information. The most commonly used quantitative values are derived based on animal experiments. And of course, these experiments are performed on animals at relatively high doses, and you have to take the adverse health effects that are observed in animals and extrapolate them or interpolate them to human beings. And how you do it is again a policy choice. Although the experiments are done in a very in a technically uh, manner which has very strict technical protocols, uh, and the observations are technical, how you observe whether the animal is getting cancer or its liver is affected. But then when you extrapolate to human beings, there are a variety of models that's out there, and US EPA has selected one particular model. And there are some different sources, databases where you get information. So the next two slide, next please. And these are the terms that are used for quantifying the non-carcinogenic effects of chemical. And then the next slide gives you the quantitative toxicity factor. Next, please, for carcinogenic effects. So these are the factors that are developed based on primarily animal experiments. Next. So then the next question is: we know the dose, we know how to calculate dose, we know what the toxicity is. We can go to publicly available databases to get the toxicity values. How do we combine them to calculate risk? And for non-carcinogenic and carcinogenic effects, there are different ways to quantify the risk. For non-carcinogenic effects, it's simply the ratio of the dose divided by a reference dose. And in the next slide, and it's called the hazard quotient. In the next slide, we have the individual excess lifetime cancer risk, which is the product of dose and slope factor. And this represents the probability of the individual who is exposed to that particular dose, um, the probability that he or she would get cancer during their lifetime. Okay, so to summarize what we have, what I have been speaking is, this is a schematic which says that risk depends on toxicity, exposure factors, and exposure concentrations. And in the when you are developing standard, you are actually doing that in the backward mode at the bottom of the slide, where the acceptable risk is a policy choice, and the toxicity you get from publicly available databases, which is specific to the chemical. And then you use policy and site specific considerations to get the exposure factors. And then you end up with the unknown is exposure concentration, which is considered to be the risk based standard at the point of exposure. Okay, so the trick here, or the complicated thing, is not the science, not the mathematics, not the calculation. The ninth grader can do the calculation. It's the policy that is necessary to select an acceptable risk, and to select exposure factors, and to account for the variability that exists in the population. Next, please. So now the equation I showed and the method I talked about will help you develop the POE concentration at the receptor location. But many times the question is, but what is the acceptable concentration at the source? Because I want to make sure that what is emitted in the atmosphere is safe for the receptor, who may be half a mile away, or 50 or 500 meters away. So in order to do that, you have to factor in the migration of chemical from the source to the receptor. And that's the part where what we call fate and transport modeling comes in. And that depends on the source and the media. Let me give you a few specific examples. Next, please. So these are just couple equations I threw in. This C over here is the indoor air standard TCR is the target cancer risk. That is a policy choice. And then all the other factors, how long you are there at breathing that air and how many hours in a day you are breathing that particular air and so on. So this is for carcinogenic effects. The next equation is for non-carcinogenic effects. Next. And Vito, you can look at these later. Next, please. So these equations, the air concentrations, would give you the acceptable concentration at the point of exposure, which is the receptor breathing the chemical that may be emitted from a chimney or a source, it could be a point source, it could be aerial source. So now the question is, how do I develop a standard for what is the acceptable emission at the chimney? Or what is the acceptable emission from a facility which has multiple point sources of emission? There may be various valves that leak, there may be multiple chimneys, there may be multiple other sources. So in order to calculate that, you have to account for the transport of chemicals from the source to the receptor and the decrease in concentration that happens over that distance. So this is for air. Next, please. So you can also ask the question, if I have impacted soil, let's say a landfill, or I have a facility that has spilled some chemicals and the soil is contaminated, and 100 meters down gradient from that source is a drinking water well. So the acceptable concentration at the point of exposure can be calculated based on risk, exposure factors, and toxicity. But the question is, you have to use that concentration and try to back calculate using modeling an acceptable concentration in the soil source. Next, please. Similarly, you can ask the question, if you have a manufacturing facility, you have a refinery which is close to a river, what is the acceptable concentration at the source in the refinery that will be safe for the point of exposure, which is the river where somebody is fishing? So the exposure pathway would be the ingestion of fish in the river, or if there are people swimming in the water, the receptor would be, or the would be the human being who is swimming and dermal contact with that contaminated water. So you could back calculate what is the risk-based standard for the surface water, and from there you can back calculate what you can allow at the source. Because the reason why you need standards at the source, because that's where you have lot more control than at the point of the receptor. Next, please. So there are many other cases. If you have a residential community next to a refinery and the groundwater below those residences is contaminated, there may be concern that benzene and toluene and other volatile chemicals may migrate upwards, diffuse into the house, and cause risk. So in the last 15 years, this particular pathway has been the driver of cleanup in the US for many, many sites. I think, and I should also say, the development standards not only depends on policy and science, but it also depends on the socio-economic factors, because cost has to be factored in this entire process of developing standards. Next, please. So the general equation, I showed you a general equation previously. The general equation for risk-based standard developments is risk depends on the toxicity. It depends on exposure factors. That's what we talked before. It also depends on chemical specific properties, the volatility of the chemical, the mobility of the chemical, the biodegradability of the chemical as it migrates from the source to the receptor. It also depends on the media properties, the distance from the source to the receptor, the wind speed, the wind direction, the inversion layer, the hydraulic conductivity of the soil if you are dealing with groundwater, or amount of flow in the river if you are talking about contamination or surface water standards. And these factors then are also linked with the point of demonstration concentration, which would be the risk-based standard. So this is one equation where if you it has 1, 2, 3, 4, 5, 6 sort of parameters. If 5 of them are known, the sixth can be calculated. And obviously, in the old days, we used to use simple calculators and slide rules in my college days. Now, of course, you have very fancy software that can easily do the calculation. So doing the calculations is not an issue today. Understanding the what goes into the calculation is the big challenge. Next, please. So from a computational perspective, you have to have a model that tells you how chemicals move from the source to the through the media, how they get to the receptor. Then you have to have the uptake module which estimates the dose, and then you combine that with the toxicity to calculate the risk. So this is sort of the computational process, which is, as I mentioned, is relatively straightforward and easy. The tough part is the policy choices that have to be documented and clearly understood by everybody. As you know, in the US, we have been dealing with this sites at least for the last 30, 40 years. Billions and billions of dollars have been spent, millions of them in research, and still the policies are not clear and they keep changing. So I have just a couple more slides and then we'll have questions. Next, please. So I just wanted to show you a couple of risk-based examples of risk-based standards. So I took 3 chemicals: benzene, arsenic, benzene, which is a volatile organic chemical, a solvent also, a constituent of petroleum, as you know, arsenic, which is uh, metal, which has been a source of a lot of risk in many situations, and dieldrin, which is a pesticide. So whether it is a VOC, a metal, a pesticide, you can do herbicides. I have shown here some risk-based standards, and you can see that I've shown you standards for soil in milligrams per kilogram, air in microgram per meter cube, and a tap water standard for residential water supply. And you can see for benzene, the standards are different in residential versus industrial scenario. And the reason for the difference is the exposure factors are different. The toxicity of benzene to me as a resident, if I'm sitting in my home, is the same as if I am in my office. The toxicity is the same, but I spend different amounts of time in the workplace, different amounts of time in my home, and that's what causes the numbers to be different. So next slide, please. Uh, so these are the kind of a summary of all the factors that go into developing risk-based standards. Some are policy choices, some are scientific, simple science, complicated science in some cases, and superimposed on all this is the socio-economic situation, because cleanup of site, implementing these standards can be a huge cost, and doesn't matter whether the industry pays the cost or whoever pays the cost is public. It's we all pay that cost in one form or another. So And then that's all I have to say. I have one other last slide, which is my next, please. Yeah, this is my favorite slide. So I'll stop here, and you are welcome to ask me any questions. Also, Professor Nagendra, if you'd like to share my email and telephone number with anybody, and if they would like to send me an email and ask any question, more than welcome. Thank you very much.
Thank you, Dr. Atul Salhotra. It's very excellent talk, very interesting. Let's see that. Do you have any questions? Could you please, any questions from the participants? Please type your questions on the chat box. Dr. Atul, a very interesting way to look at it. Maybe I'll just stop interesting to look at it.
No, I can only hear you through my cell phone, unfortunately. So please turn it off.
Okay. Yeah,
I'll call you
okay.
again.
Sure. Okay, so these risk-based standards are quite important in terms of understanding the impact. So, what do you think from the ambient way? For example, we have in air quality standards.
Yeah.
Where people spend different time in indoor, outdoor, and transport, travel. So in different time periods and different space.
Correct.
How do we develop these risk-based standards?
Well, so I think the way to do it, sorry, I'll have to mute this. So I think the way to develop these standards is to start with a, I think it has to be specific to the area, specific to the facility, and the nearest receptors, if they are residences versus non-residences. And from there, you can back calculate what would be allowed as an emission source. I mean, that's one way to do it. Uh, there are monitoring stations in many parts of the country. You have to measure those and compare them with whatever the exposure standard is in that area. So if it's a residential community versus a industrial facility, the standards would be different. So it's not an easy problem, and that's why most of the air standards are mass based. As a permitting process, you say how much is allowed to be emitted, but they are also based on modeling that has been done to see what the risk would be to the population surrounding that area.
Okay, so the other question comes to my mind is since the exposure happens, for example, let's take benzene. Benzene may be available in water, benzene may be available in soil, benzene may be available in the air, but the amount of exposure we happens, for example, amount of air we inhale, the food we consume, and then maybe the dermal interaction. So how do we bring out all these aspects with reference to age? Yeah, for example, particular location may be dominated with aged people. For some area, it will be dominated with a younger generation. So how do we make these standards more normalized?
Yeah, so there it's a very complicated way to implement these. If it was easy, we wouldn't be here. But the standards can be developed for a child, and it can be developed for an adult. So if, for example, you are in the school area, the in a high school or a middle school or primary school, you would look at the standards for the child and you look at standard for the adult, and the one that is the lower becomes the standard that you would shoot for. So there is this concept of screening level standards, which are very conservative and applicable everywhere, and then site specific standards, which are only applicable to that particular site.
Okay, that's good. Yeah, got it. So coming to the model will have there are different types of models these days, and even if I try to look at it, the probability of risk calculation is also a probability.
Yes.
So maybe our models are more like a conventional models are more deterministic in nature. But what do you think? Because the current AI, ML, machine learning, these kind of models will add value to the forecasting or prediction purpose.
Yes, absolutely. So first of all models are wrong. Some are useful. Okay. The only model that really matters is the real world, which nobody has been able to model. So you can approximate it, but there is no unique approximation. 2.1 is an approximation for 2, and 2.11 is also an approximation for 2. So there are infinite approximations. So there are almost infinite numbers. When I teach my 2-day, 3-day course, I tell my students the number of models is directly proportional to the number of graduate students and professors, because everybody is pushing this envelope of science and making some changes, and the everybody is developing a better model, and that will continue. So I think the machine learning and AI will definitely help, but at the end of the day, the policy choices are very critical. And to make policy choices, given the variability and the uncertainty, is the big challenge, in my opinion. Science is easy. It's there's a lot goes into science, but we have a lot of good scientists in India, in US, everywhere. We can make good approximations, but it's the policy makers that need to step up and make the right policy.
Okay. Yeah. Dr. Atul, can you just see that whether you can able to see some comments chart section so that there are some questions? Otherwise, I will read it from here. But if you can able to read from chat box, then it's go. Okay.
Let me see.
May I
No,
ask
I
you
don't
some
see
question?
any. I don't see any questions.
Okay, I'll read it. Okay, Gupta ji wants one question. Yeah,
Yes.
so Gupta ji is also very supportive of air quality management lecture series. Yeah, Gupta ji, go ahead. He's also an eminent industrialist in India.
Yes.
Sir, very nice presentation you made, Atul, Dr. Atul. You made a very nice presentation, and it was very enlightening. I will just refer your attention to your earlier slide, one of the earlier slide, which you mentioned, source, media, and receptor. So it is very easy, and it is also easier to develop a standard. The the problem is the most complex problem, and people don't understand this media. It is a very complex relationship between the pollutant and what happens between before it goes to the receptor. So this media is the whole real problem actually, and we are making approximations, and our understanding of this complex relationship between pollutant and nature is very complex, and we have still not been able to understand it fully. And because of this, all these issues arise, and we have never been able to achieve any receptor standard in any country so far. We have been able to achieve standards or reduce pollution from the source based standards, but receptor based standards we have never been able to achieve anywhere, I think, in the world, entire world. And this issue is only because our understanding of this media is very weak, and we are not paying enough attention on this. And I think we have to strengthen this our understanding of this media part. Then maybe we will be able to make more realistic, I would say, standards. That is
Yeah.
my observation on this.
Yeah. No, that is.
Okay, Victor, thank you. I think you are right.
I think absolutely correct. We need to spend more effort to understand the properties of the media and the natural variability in those properties,
Yes,
because there is nothing we can do regarding the variability. We just need to learn to address it. We
yes.
can, rainfall in which, I don't know which town you are in, but I'm in
I'm in
Spokane.
Delhi, not
The
North India,
rainfall
Delhi.
in Spokane is variable. We can
Yes,
put 20 rain gauges and we will get a better estimate of the rain, but we are not going to be able to change the variability that is inherent
yes,
in the rain. So
correct.
that's where we have to make good, solid policy choices to understand the variability and to be able to quantify the variability. There are many statistical techniques, Monte Carlo simulation, sensitivity analysis that we do in modeling, but it's a lifelong endeavor to continue to improve on what we know. So you're absolutely right. So I
Thank you.
Yeah.
can see the chat box.
Okay, go ahead.
Mr.
Then it's
Swami, the
fine.
models are quite simple, direct exposure based. Can they account for cross media exposure situations? For example, when you have a green belt in the case of a chimney emission. Yes, so that is the media. So the description of the media in this case is there is a source, there is a green belt, and then there is a receptor, and the green belt will hopefully reduce or diminish some of the effect of what is being emitted. So yes, those can be taken into account. Uh, let's see. I don't know if I answered the question. If not, please, you can ask again. Priya Verma, what should be the basic criteria for selection of parameters model for risk assessment analysis? Well, to be honest, I don't know which particular parameters and model you are referring to, but as far as models are concerned, in a regulatory environment, regulator sometime policy specifies thou shalt use this model, and then that's your choice. The regulators help you with that choice because that's a policy choice. And if the policy is keeping up with the times, they will pick the right model, the most appropriate model. As far as parameters are concerned, you have to decide whether you are doing a worst case calculation to calculate risk, or are you trying to calculate risk for the average person. So depending on that, the parameters would change. And also, there is the idea of sensitivity analysis. I don't know whether someone breathes 15 meter cube a day or 25 meter cube a day. I'll do my calculations for both and I'll get a range of risk and see how that works out in the situation. So it's kind of like saying, if I'm staying at a hotel, airport is about 20 minutes away. If I talk to five people, one guy will say 20 minutes, another guy will say 25 minutes, somebody will say, oh, it might take you an hour because you might get stuck in the traffic. So there's variability. And I have to decide what is my risk tolerance and accordingly make a decision. The decision that I will make, I can tell you, is very different from the decision my wife makes. When I'm going to the airport, 1 hour is enough. But for her, 2.5 hours are minimum. Because, and that's nobody's right. It's just the way we think of risk. So that may, in some way, answer that question. Okay, uh, Mr. Mitra, we conduct risk assessments for air inhalation, water ingest separately. Use is there any way to estimate the synergistic risk instead of performing individual? This is a very, very interesting question. We talk about synergistic risk, and synergistic is 2 plus 2 equals 5. Okay? Additive risk is 2 plus 2 equals 4. Potentiation risk is 0 plus 2 is, no, 0 plus 0 is greater than 0. Okay? And then there is the other case where 2 plus 2 is 3, because there is counteract influence. So there's a lot of discussion on synergistic risk, and there are only a few combination of chemicals for which we have scientifically shown that 2 plus 2 equals 5. And one of them is if you smoke and if you get exposed to asbestos. Smoking and asbestos is a worse combination than just smoking by itself and asbestos by itself. So for some combination of chemicals, synergistic information is there to calculate synergistic risk, but for most it's not available. So you end up calculating for individual chemicals. The second part of your question, is it correct to carry out carcinogenic, non-carcinogenic separate for air, water, and soil, and then sum them to obtain an overall value? What would approach lead to an overestimation? Would that approach lead to an overestimation of risk? So if I drink water that is contaminated with benzene, my route of exposure is ingestion of benzene, so that will translate into some risk to me. Now, if I inhale air that has benzene, that is inhalation exposure, and that will also contribute to risk to my body. So that if I drink water contaminated with benzene and breathe air that is contaminated with benzene, I will have two routes of exposure and I will have two sources for risk. So I have to add them together. Now, there are some chemicals that are only carcinogenic by inhalation, but not by ingestion. So there are some cases like that, but in general, if something is carcinogenic by inhalation, it is carcinogenic by ingestion, and so you just add it together. So, and then that part is easy. The difficult part is, what is acceptable risk? Is it based on each pathway, or is it the cumulative risk that you have to compare with the acceptable standard? So that gets a little bit complicated. But yes, you separately calculate the risk for each exposure pathway, and then you add it together to come up with the cumulative risk. And that's for different pathways. But typically, we may be exposed to benzene and benzoapyrene, which are both constituents of diesel, for example. In that case, we have to calculate the risk for benzene, the risk for benzoapyrene, and then add it together to come up with the cumulative risk. So at a given site, there was a study done for Superfund sites, which are the very contaminated sites, very large site, sometimes tens of square miles of contaminated land. And in those cases, um, in those cases, we have in the US, there are actually about 20 chemicals, industrial chemicals, that cause the most risk. And so there is a way to select the chemicals of concern. And, although there may be 1,000 chemicals in petroleum, only 5 or 6 contribute the most risk. So that's how we limit the risk. And would that approach lead to an overestimation of risk? most of the risk calculations that we do, they do end up with overestimating the risk a little bit. Because at the end of the day, we are talking about human health, so we have to be conservative. So taking a little bit more precautionary approach is probably the preferred approach. Okay, I hope that helped your answer. We have Kishore. Is there a method to calculate risk assessment for if I have a data of chemicals, toxicity, boiling point, volatility? Yes, absolutely. If you send me, so the answer to your question, Mr. Kishore Kumar, is the yes, there is a method to calculate the risk for air quality, and certainly if you can share some data with me, I'll be glad to help you out and or give it to Dr. Shiva, and he will definitely be able to work with you to calculate that risk. Krishna Prasad, should the risk-based standard be based on worst case scenario or an average? Well, we have been debating that issue for 40 years in the US, and we haven't found an answer. What I tell my clients and what I do is, if it's a complicated site, calculate the risk for the average case and the worst case, and then make a decision based on that. It's like traveling to the airport. Somebody says it's 1 hour, somebody says it's 2 hours. Okay, I'm just to allow myself 1.5 hours. So you just, and that depends on the risk acceptability of the individual. I think I answered all the question. Any other questions?
Yeah, there's one last question is there.
Mr.
Maybe you can.
Mukherjee, how bioassays is connected to the chemical exposure addition? So bioassays are used to quantify the toxicity of the chemical. Additionally, how it is defined as sole chemical exposure or mixed I think we answered that. How to characterize the factors. I think we answered this question.
Okay. Yes.
Mr. Swami has a
One
question.
more question.
The risk
Yeah.
assessment is human health focused. Can these be used to calculate ecological risk assessment? Yes, we do ecological risk assessment. The process is exactly the same. The bird eats the earthworm, and the earthworm has bioaccumulated pesticide, and so the bird gets exposed to that pesticide. So the calculation of risk is similar. The problem with ecological risk assessment is that the receptor is not clear. Are you in the human health risk assessment? We talk about individual excess lifetime cancer risk to each individual. But in the ecological risk, we really don't care about one bird. We care about the ecosystem. We don't want we want the ecosystem to thrive. If one earthworm dies, nobody cares. But the ecosystem should be able to sustain the earthworms. So the thinking is a little bit different. There are multiple receptors, and my colleague, I think he's on the call, Mr. Venkat Sambana. He did his master's in ecological risk assessment and is a very key member of our team here in the US. Any other questions?
Yeah. Thank you, Dr. Atul Salhotra. It's excellent. The discussions were quite interesting, as this is an area of interest to everybody, and it is also growing in India. So thank you very much. Before we close, we will also take one photo with all of you. Can start your camera video so that we can have an online video. And anyway, Dr. Salhotra will going to visit us in Delhi for IASU conference.
Yeah, I'm looking forward to that visit and that conference, and looking forward to hopefully meeting some of you.
Yes. Done, Ashwin? Yeah. Thank you, Dr. Salhotra. And so nice of you. And it is quite late for you. And it is irrespective of time difference you paid. And I think Dr. Sengupta is also there. Very good morning, sir.
Good morning, sir. Good morning. Good morning.
Dr. Salhotra, Dr. Sengupta was a member secretary for CPCB for more than 10 years.
I see.
Well-known person in India for the hair quality management. And he's the first one to start this hair quality management lecture series.
And where are you physically located?
I am located at New Delhi, sir.
Where?
And you'll also
New Delhi.
Yeah.
Delhi.
Oh,
He's at,
Delhi. Okay.
Delhi. Yeah. Okay. His speaker has some issue, Dr. Sengupta. So that's why I'm just trying to ease you. We are on the WhatsApp call.
Yeah, look forward to seeing all of you or some of you, and again get my telephone number and email from Professor Shiva, and we can communicate.
Sure.
Yeah. Thank you, Dr. Salhotra, and yeah, very good evening to the rest of you, and yeah, have a good night to you.
Good night.
Okay. Bye-bye, and thank you all for joining the Air Quality Management Lecture Series. See you in the next month lecture. Thank you. Have a good day.